Hey everybody! The purpose of this video is to get us to some solutions to our logistic regression quiz on the world population. So the first thing we're going to do is we're going to get a nice logistic, which is that tempered exponential growth model for our data. So we're going to enter this in. We're doing population as a function of years. And I told you to do years after 1800. There's a reason for that. And as I'm entering the data, I'm going to explain it to you. That's 127. And the reason is you have to do it this way because the logistic model has to creep off towards zero. It can't start at anything before zero. I don't know why, honestly. I don't understand why. I haven't studied this in years and years and years. And although I did know it at one point, I sure don't know it anymore. 199. So I'm just going to make it's kind of along the same lines of that idea as why you can't have zeros in the exponential model for y values. Oops, that's not right. That should be 224. And then 242. And then last but not least, we slap in the billions. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So we'll start with a scatter plot so you guys can see what's going on. Let's turn it on. Actually, it looks great. And there it is. And you can see why a logistic model does make sense. I mean, it's going to go up and then it starts S-ing off and leveling off. So the first thing I want you to do is to actually find the model. Let's see how long it actually takes on my online TI here. Logistic Y1 function. Let's see how long it takes. It takes a while on my handheld machine. It looks like it's taking a while. Oh, there it goes. It was quick. It's much quicker. It took almost a minute on my handheld machine to do this. Don't worry about what these numbers mean. They are fairly important, but they're nowhere near important enough to get you hung up with right now at this point. One of them involves the growth rate. One of them is a limiting value, which I'll get to momentarily. That's what I want to look at. Basically, I wanted you to see that it fits it most definitely excellently. It's a great looking model. Why does a logistic model make more sense than an exponential? Because in an exponential models, they grow without bound, right? Earth has bounds. And some of those bounds would be, say, resources, water, for example. Resources, water, space. Imagine if we could grow to be 1 trillion people. Well, 1 trillion people, we'd be competing for space on Earth. Water, space, food, all other kinds of things are limited, not boundless. So you need some kind of a carrying capacity model, which is what the logistic model actually how it has us do. What should the human race's population have been at the end of 2013? Okay, well, since we now have the model in Y1, we can go to our table. I'm going to set my table up like it is for you guys and go right to that table. And 2013 is 213 years after. It's saying right about 7 billion. It's saying 7 billion. It says to the nearest half billion, but it rounds to 7. I'm not sure why I said half billion. I should have just put billion. Doesn't matter. Same answer. Google thinks that right now there are 7.143 billion people. Looks like we crossed over the 7 billion mark in 2012. Not bad from what the UN said. This study was actually done back in the day, early 2000s, so they didn't do a bad job of capturing it. What's the percent error in the estimate? Well, the percent error would be the estimated value we got minus the true value, 7.143, divided by that 7.143. And what I'll do is, to get you an estimate of that value, I'll fire up a Firefox window, and we'll just let Google figure it out. And it doesn't like that. Too many spaces. It doesn't like that either. Why doesn't it like that, I wonder? Let's take out that and put together. There we go. It likes that one. It didn't like the long subtraction sign. Negative 2%. There's your percent error. Negative 2%, which means we underestimated by 2%, which, honestly is not shabby at all. Not even a little bit shabby. What is the apparent carrying capacity of this model to the nearest billion? The model tends to level off at which number? This was a fun one because this requires you to throw back to some of your old Math 95 skills. You can see this curve is beginning to level off, but it hasn't done it yet. So the first thing I'm going to do is I'm going to increase my Y max up to, say, 20. And then regraph and see if, okay, so now we're starting to see, it looks like 20 might be good enough as far as this way, but it's not good enough this way. So it's going out to 2165. Let's go out to the year 2200 and regraph. All right, I don't think that's far enough yet. Let's go out to the year 2400, or 2200, excuse me. Getting there. Let's go out to 2300. 500 years after 1800. All right, now we're starting the level. Let's go out a little bit further. Let's go out 700 years. So now we're the year 2500. There. Starting to level off. Now I'm going to do a little trick here where I'm going to go to the value command. I know this is out to 700. I'm going to go to 650. So this would be the year what? 2450. It tells me it's about 15 billion. And you can scooch the cursor as you go, and you realize as you do this, you see what happens. That value of Y is not changing very much. It's changing, just it's way far out in decimals you don't see. See those numbers right there? You might recognize them from this screen right here. It's the same value of C. When you look at this equation functionally, the value at the top is the limiting value. The stuff underneath is the rate and the changing, but this is the limiting value right here. So this guy out here, this 15 billion, that apparently is the carrying capacity of the Earth if the population of Earth is acting logistically, which is not guaranteed at all. Not guaranteed at all. But what this tells us is we can basically double, a little bit more than double our population and not exceed the carrying capacity. So we don't know because, again, we're assuming it's going to be logistic. Who knows? You have to keep watching this and watch it as it changes. So predicting that far out is a dangerous game, and it's well past our lifetimes anyway. So I hope this helped you get some answers, and we'll catch you in class.